Today we have a slightly different beginning of the lunch. We will start with a Q&A with Rai Weiss, who recently, this year, was awarded the Nobel Prize, and we have some questions for him.
I'll give it back.
We told him that he doesn't need to prepare. The questions will be completely spontaneous. And then we'll move on to the standard format. But before we get to the speakers, I wanted to mention that Eric Kito very generously decided to pay for the full ITC lunch in this academic year. And we are grateful. As many of you know, Eric provided funds for the Kito Prize, which is awarded once a year for the best PhD in theoretical astrophysics. That is endowed, and that's part of the ITC. But he decided that this forum, he finds this forum so exciting and important that he wanted to fund it for this academic year. And we are very grateful to Eric. Let's thank him for that. And as a small sign of gratitude, we'll give him another ITC mug. But inside this mug, there are chocolates. And if you look at their title, the label says excellence. So there are lots of chocolates that will remind Eric of the excellence that he brings and that all of you bring to the ITC.
Oh, thank you.
And we just heard an excellent ITC colloquium by Wyn Evans, who will speak a little later. Today we'll have, after the discussion with Ray, we have Wyn speaking about HEX. He will tell us what this means. I don't know. And then we'll hear from Anna Schauer from Heidelberg. Is she here? Oh, great. And she will talk about Lyman-Werner escape fractions from Minihaloes in the first Galaxies. And finally, we'll hear from Jordan Keller, who should be here. He is a Black Hole Initiative postdoc. And as you know, the Black Hole Initiative combines people from astronomy, physics, math, and philosophy. So Jordan belongs to the brand that is associated with math. He will talk about the mathematics of linear stability of Schwarzschild black holes. So Ray, please come over. And I will start with a few questions to Ray.
Oh, God.
These are really...
Oh, you want me to stand up?
No, just sit here. There is a chair.
Oh, this chair?
Yeah. Have a seat.
All right.
And this is a mic that you can use so everyone can hear you.
Okay, good.
So, was it difficult to explain the physics associated with LIGO and gravitational waves to the royal family?
Did you hear his question? Yeah. He asked how hard it was to explain. Is this mic working?
Well, it says it doesn't. Okay, so you want me to repeat louder? Okay. The question was, how difficult was it to explain the physics? The physics of LIGO and gravitational waves to the royal family.
Oh my. You got the question now. I didn't meet them very much. I mean, I'll tell you what my biggest fear was, and I'll not answer the question by answering a different thing. That's the way. And the way I'll tell you, the thing that was very funny and complicated was that, when you have this, I mean, I've never been to one of these. I never had ambitions to be in a place like that, but it happened to be. I was there. Okay. And so what happens was that the king was a little bit older than, well, he's probably a little older than I am, or maybe just about. And I thought he was maybe a little bit dottery, okay? And so I was worried that he was going to hand me this fairly heavy, manuscript thing that has a plaque as well as a gold thing, okay? And I felt, no, that's not way enough. So I was figuring, I was walking toward him, and I was the oldest. I don't know if you know this, but this is is the prize that has the highest cachet. So physicists always go first, and the oldest physicist goes first. So that's the result. And I'm the oldest, I'm 85. So what happens, I had to be the first to go into to talk to at the ceremony, and I was very worried. What I was deeply worried about is that I might just pick the thing wrong and we would drop the damn thing. And then we both would sort of going down like this and have our hookers hanging out, looking at the audience, and it would be kind of embarrassing to screw the whole thing up like that. And so I kept worrying, how do I grab it so that he doesn't fall and I don't screw it up? Okay, we managed that. And so that was the thing that was occupying my walk towards. So we didn't have a conversation. That's the first thing. Then on the way back, I had a sort of complicated thought, and it turns out Kip Thorne had the same thought. He says, what in hell am I doing here? Walking that same thing a family did? It's crazy. I don't belong in that group. That's completely nuts. You know? And this whole thing of, my God, who has walked all that path before? And that left both of us, in the end, sort of awestruck. Okay? We have no business here. That was it. So so we never really had a conversation with the king. Okay.
Okay, well, for us, imposter syndrome, exactly. And as far as we are concerned, you deserve that place more than many.
Well, all right, leave it go. But I mean, that's what you asked. What was going on? That was the conversation that I had with myself. Okay.
So now a little more difficult question. Given that you pioneered, what we can do is just hold it.
Okay, I hold it. You hold it.
Given this brand new field that you pioneered, what do you foresee for the next 10, 30, and 100 years into the future? This is recorded, so people will compare notes.
Well, I'm supposed to say a little about that in this talk this afternoon later. I hope I say the same thing here as I do there. But it's very clear there's a new field that's opened. I mean, I think even the NSF understands that now. It isn't just the detection of gravitational waves and it's over. I mean, I was very deeply worried about that all that technology and all that stuff would be looked at as a one-shot deal. An experiment and the experiment worked. So now, a lot of people have been looking at this, what might be the next big things that come out. And of course, we had a banner year last year, which was completely wild. I mean, we'll talk a little about that this afternoon. I mean, that neutron star binary, and then the fact that Virgo was on the air with us and we were able to locate the black holes better. That's sort of the beginning of a whole thing that's now going to happen. I said to my colleagues when I walked in, after all these two events in 1 week, I said, oh, God damn it, we're going to see a supernova tonight, right? Okay. And that's why, that's another thing that's, of course, much advertised and hopefully we will see sometime. But then the thing is, you start looking at what new things can be done, and especially the people who are looking at what new detectors are worth building, at least from our side. And it looks like you can do some spectacular things looking at the whole universe in black holes. I mean, it needs a somewhat better detector than now, if you want to look at the whole universe. But that's going to be a fantastic thing on its own. You're going to have, not only doing cosmology, but you're going to find out when did they come from, where did they come from. I mean, you guys must have been thinking about that a lot now. I mean, that's a deep problem. And we'll say more about that later. I have no wisdom on that. But at some point, maybe you'll find out it ends. There are no more black holes, and that would be wonderful to find out. Or you might find out it doesn't end. I mean, I rather doubt that. So that's one thing. And then I still hope that there will be something we can see in the cosmic background. I mean, I know the B modes, I wish them luck. I really hope they succeed with this. But if there's something there, it would be wonderful if you could see it. Now, that may not be possible with the detectors now. I don't know, unless it's really very much larger than people thought. But I think it's the most spectacular source that you could look for. I mean, I don't know, all of us have been thinking about that. And then there's all sorts of things which, the Kip, if you ask Kip this question, I'll answer for Kip, because I've talked many, many years with Kip about this. And here is a standard Kip answer, okay? It's a wise answer, but it doesn't answer it completely, okay? And what it is he says, look at all the things that have happened in electromagnetic astronomy. Every time you open a new field, I mean, we open X-ray astronomy and you find out the universe, or radio astronomy, you find out the universe isn't placid at all. It looks like a hellhole. I mean, all sorts of crazy stuff is going on. And so now here you have something which is completely different. It's done by masses that be accelerated, not charges that are accelerated. It gets through everything. And so you ought to find things that are new for that field. I mean, there are two pieces to that. You will look at old things you already know and know them better, and that's a supernova, for example, or even the neutron star, which binary. But there'll be hopefully some kinds of events or some kind of phenomena that you haven't thought of. I mean, that's generally been the case. But I can't tell you what they'll be. I mean, I'm hoping we'll find that the wormhole exists somewhere out there, and there you're looking into another galaxy. I mean, into another universe. Okay. I mean, and you know, I'll tell you something. So one of my colleagues sort of said he's already looked at the distribution of black holes. I mean, now we only have 5 of them, right? And I mean, 5 of these things. So you know, it can do some statistics, and it looks like there are too many of them in the southern hemisphere. Have you noticed that? No. Okay, now take a look. It's already getting a little embarrassing.
I see. Well, you actually answered my next question, which was what kind of unexpected sources.
I don't know all the
but if from an instrumentalist point of view, I mean, obviously you had to work very hard to convince NSF to provide the $1 billion for this to happen. If you had all the money in the world, you know, $1 billion is not a lot by Silicon Valley standards these days. If you had all the money in the world, what would you do with it? What kind of an instrument would you build?
An instrument?
Yes. Oh, no, I did. Of course. Yeah. This was not such a general question.
Oh, my Lord. That's an interesting question and a very hard question. I mean, clearly I have some interest in finding out what goes on at higher energies in high energy physics. I would love to see a linear collider being built. That looks like that has not directly to do with us, but it has indirectly to do with us. And we have an idea already which is going to cost billions for this field, and that's I'll talk a little about that at the talk. In other words, a much larger version of LIGO. And I clearly think that the thing that you do in space, and that's going to happen. We're going to talk more about that later. People are spending their billions, at least in this field, that are thinking about the right things to do, I think. And it's really the fact that you have so many different phenomena at different frequencies. You know, I mean, the ground isn't the only place you want to do this. You want to do this. I mean, you want to do this in space. You want to do it. In fact, every one of the ideas that's being pushed, like the B modes, the pulsar timing, and the ELISA and the underground things, they're all complementary and very interesting. I don't know. I can't answer your question directly. Give me $1 billion or more than $1 billion. We're going to be asking for $1 billion at some point.
Right. But suppose even more than that.
Yeah. Well, yeah. That's. No. Let me tell you that $1 billion that we got already from the NSF was here's something that everybody in the room ought to know. I want to not be able to say that. I said this very publicly other places. The NSF took an incredible gamble with us. And incredible in the sense of whether you look now at the way they operate. Not the way they were operating back in the 80s, okay? Or in mid-70s when this started. And the thing is that the gamble is deeper than you might even think.
How do you explain that?
Well, I can explain it. I can explain it with one very simple fact. We had a mole.
Who was that?
Richard Isaacson. Richard Isaacson was in the NSF. He was an expert in this field, had done his thesis with Misner. And he had the idea that the NSF, and this was as he came into the NSF in the middle 70s, and he had the idea that doing the Weber thing had just about settled as a null, okay? But he had the idea that this field, with a new technology that had come in, not just gravitational waves, but other things you could now test in general theory of relativity, which you couldn't have done 100 years before. Okay, when the theory first came out, I mean, I'll say a little about that in the talk too, but the thing is that now was an epoch where you could begin to actually challenge general relativity with experiment. He was thinking very deeply about that. And he thought that was exactly the right thing for NSF to do. And he convinced Marcel Barden, his boss, of that, who was a high energy guy, at Columbia, like nuclear physicist. And the two together made a team that just pushed through. And I'll give you very good examples of that. When an administrator in a government agency wants something, You arrange things properly, okay? You get the right reviewers, okay? You make sure that the people who are pleading the case know that they shouldn't do certain things and they should do other things. You guide the people who are doing the science. And that's what he did. He was not only he was the advocate for it in the NSF, but he was also the organizer of us silly people on the outside. So that was critical. But the other part was that he managed, despite that, to fight a battle which really was a very hard battle. We didn't have the technology ready, although we thought we did. And the theorists didn't have the sources in their heads right. I mean, the idea that, early days people were thinking of supernovae. And eventually became compact binaries, but only after a while. Okay? And so the thing is that we couldn't have gone out and advertised that we had guaranteed technology and guaranteed sources. And here we are asking for a big deal. That was the real gamble they took. Yeah.
So perhaps the lesson from that is that we should encourage many of our students and postdocs to enter some offices in Washington and advocate for the science that we all want to be funded.
Very intelligent leadership in the government is absolutely needed. We don't have it right now, but that's enough.
I would like to open the floor for questions from the audience.
Erwin first.
Just one question about, you mentioned space, and I thought of Lisa, and I was wondering what the status and prospects are with Lisa.
Okay. I'll talk a little about that in my talk, but I'll tell you what I'll say. Lisa, as you know, was started as an American project, and then it became, back in the 70s, it's almost as old as LIGO. And what happened is that it was studied both by JPL and then by Goddard. And it became the last decadal survey gave it a high priority, but not the first priority. And that was always considered a negative point. It wasn't the very first thing everybody wanted to do. It was quite clear that astronomers didn't yet realize that there might be this really wonderful field that's coming. So W first was the thing that was the more important. And so that held things back. And then the budget travails that happened under Obama with the Republicans refusing to put money into the government at the time really caused NASA to cancel their contribution to LISA. I don't know if you probably knew that. And that happened. And so what happened is that by that time the Europeans, especially the Germans, were pushing a lot of the technology in LISA, and they were deep collaborators. And so they decided they thought they could do it alone, which I think is a mistake, but that's just my own opinion. And they then kept the thing going. And this last mid-decadal survey that was done managed to get NASA, partly because of our success. It has very little to do with LISA's sources, but the fact that now there was finally gravitational waves detected. That was important to the administrators at NASA and other places as well in Congress. And so consequently, what happened is the mid-decadal survey made a recommendation that NASA should get back into it. And that happened. And now I can only tell you they're not fully into it. But there is negotiations going on with Europe about being the same kind of partner they were in the beginning. And the negotiations have to do with, should the Americans bring in an instrument, or this is a standard way that these collaborations get made. So right now the Americans are buying their way back, or trying to get their way back into it. The European councils have given it enough of a priority so that they want to launch a LISA-like mission in the mid-30s. And the people in Europe want to do it earlier than that. They want to do it in the end of the 20s. And that's the best I can tell you. There's been one more thing. I'll show you the data if I have the time in the talk. They had a Pathfinder, the LISA Pathfinder, which was a huge success. And I'll show you that success. Okay.
There was this joke. I was on the review committee that actually Ray presented to a few years ago before the detection of the first gravitational wave source. And back then, everyone thought it's a physics experiment because it's basically... it involves physics and it's a laboratory experiment. As soon as a source was detected, it became an astronomical observatory. Right. So that's the transition in the minds of people at NASA.
Well, it was more than that. It was more than that. You're right. I mean, the transition into astronomy, in fact, is now going on. And in fact, it makes things a great deal more complex in terms of trying to figure out how you plan the next stage. You involve the astronomers in it, and then they're very jealously they want money for their telescopes. And here's money needed for what was once a physics experiment, now turning itself into a slight bit of astronomy, a little bit of astronomy. So anyway, it's a very interesting time. Right now, there's a transition taking place. But the thing that was really true, and I remember having this talk with the guy who was chief scientist at NASA during the Obama years, and he was the astronaut, John Grunfeld. That's right, Grunfeld. I was at a meeting, and he was very blunt with me. He said, there was no chance that you would ever get a LISA mission until there had been a detection of a gravitational wave, because we didn't believe that they existed.
Really?
Yeah.
Well, he's not there anymore.
Well, no, exactly.
Anna?
Yeah, so, well, considering that you started working on this in the mid-'70s, and the first detection wasn't until 2015, what was your initial reaction when you guys finally detected gravitational waves?
Yeah. That question of the 40 or 50 years of development, a lot of that people ask that question. A lot of the press asks that a lot. I have one answer for you. That isn't exactly a direct answer. And that is that, of course, let me just say, I give you a little bit of a direct answer. We were skeptical. And that's not because of that. It looked too good. That was one of the problems. You'll see a picture of that again in my talk, and you've seen it before. But anyway, I want to point out some things about it. But we were skeptical, and then we started making up complicated reasons why we should be even more skeptical. And but then eventually we bought it. It took a while. But the thing is, though, I want to tell you about the 40 years, okay? Because that people make a huge fuss about that. And it turns out those 40 years were wonderful. They were an absolute pleasure. Why? Because it's fun to work, at least for some of us, it's fun to work on technical things. And you make a circuit and it works and you get a tremendous pleasure out of it. And you go to your buddy next door to you and say, hey, let's go out for a beer. Let's celebrate. Okay. And you have, that's why you're in science. At least so many of us are. We gotta get a big kick out of the fact that developing the technology and making progress is the thing that sort of keeps you going day by day. And that you're working with convivial people who feel the same way. So it's not an endless thing of, oh my God, we haven't detected a gravitational wave yet. That's not the way it goes. And a lot of people have that misconception. I'm sure you don't, but that's what they make out of that 40 years. They say, oh, how did you live through that?
Well, as it turns out, the 40 years were a theoretical prediction, because there is actually a biblical story about 40 years before getting to the promised land. But we need to move on. Thank you very much.
You're quite welcome. Thank you.
So the next speaker is Wyn Evans. You should put this on.
I think I can speak probably fine.
No, because it's recorded. So
Because what?
for the recording.
Okay. So I'm going to talk on halo expansions, and when I emailed my friend Alaa Tumra, he said, downright dull. Beware, about 95% of the audience will consider basis functions downright dull and incomprehensible, unless leavened with many jokes, a mixed feat virtually impossible to pull off in 10 minutes. And what a terrible email. 95%, it must be 99, surely. So why? Here is a fire simulation, feedback in realistic environments. And so this is a simulation of what the dark halo of our Milky Way might look like. Of course, the simulation is N-body and hydrodynamics. I'm just showing the dark matter particles here, and we're interested in describing how the shape of this dark matter halo changes with radius So it's becoming more elongated and elliptical. This is a box on a huge scale. It's 500 kiloparsecs on one side. But we know that we will have data very soon from, for example, the Gaia satellite on how small structures in the stellar halo are merged to give us the halo of our own galaxy. And so we want to describe expensive galaxy formation simulations simply. And so they can be decomposed simply enough with basis functions. In other words, you're replacing the positions and velocities of many millions or tens of millions of particles with about 100 basis function coefficients so that you can properly describe the shape of the changing dark matter potential. And so hex means we can compress the data. But that's not all, because you can do this with snapshots for every few 100 million years. And therefore the entire simulation can be cheaply replayed many times at will. So we can hit replay on the remote. But still, I think that's not the most powerful aspect. We can insert new objects into the simulations, and we can study their behavior as if they had been present originally. Now, of course, I can't insert a really big object into the simulation. I can't put a large Magellatic cloud into the simulation because that would change the simulation. But for sure, I can insert lots of small objects, dwarf galaxies, and substructure. And so this technique is really ideally suited to the study of the precession of tidal streams in the Milky Way galaxy, or the evolution of accreting subhalos, or satellite galaxies and globular clusters in dark halos, and the response of galactic disks to the changing dark halo potential. And all this is stuff on which the 25th of April we will receive abundant information on from the Gaia Data Release 2. So now we must do a little bit of downright dull work. We need to represent the potential and the density of a galaxy as a sum over basis functions. So the basis functions are the rho subscript NLM or the phi subscript NLM, and sums over them with the same coefficients represent the density and the potential of the galaxy model. Now, normally we want the zeroth order model to be something that looks like a galaxy, and so the higher order terms are capturing the deviations like flattening, triaxiality, or lopsidedness. And because the expansion is bi-orthonormal, then that means that I can calculate these coefficients swiftly from an n-body simulation. When the density is formed from a cloud of point particles in a numerical simulation, the integrals become sums, and so I can take the simulation swiftly and get the coefficients. So this is a cheap way of democratizing very expensive galaxy formation simulations. But to be useful, the basis functions must be expressible in closed form, and really they've got to obey a recurrence relation, so I can swiftly get n plus 1 basis function from n. Now, any such basis functions are interesting, but they're super interesting if the zeroth order model really looks like a galaxy, because then my expansion will be super efficient. And of course, there's a well-known one in the literature. It was discovered by Lars Hörnquist and Jerry Oestreicher in 1992. It's known as the Hörnquist-Oestreicher expansion. And the zeroth order model, the model about which you're building up the distortions, is just the Hörnquist model. So it's got a density that goes like 1 upon r at large radii and falls off like 1 upon r to the fourth as we go out to large distances. So that's a useful model, and it has been widely used in halo expansions, but it would be better if we had a larger variety of models for which the zeroth order density looked more general. So perhaps something like this. In the trade, this is known as an alpha beta gamma model, but the important point is simply that at small radii, the density is falling like r to the minus gamma, and at large radii, the density is falling like r to the minus 3. And so we'd be super interested in a basis function expansion in which the zeroth order model was perhaps the NFW model, where gamma is equal to 1, so the density is cusped like 1 upon r at small radii, and beta is equal to 3, so the density falls off like r to the minus 3 at large radii. So can we find such models? We can. So here I'm showing in this alpha, beta, gamma space the whole slew of recently discovered bi-orthonormal expansions. So for all of these models, we can quickly build an expansion which describes the distortion in the gravitational field, and we can use these to simply reproduce expensive galaxy formation simulations. And so there is an intersection between these two surfaces. That's actually a suite of basis function expansions that were discovered by Schauer, and the Hörnquist-Oestreicher expansion is a particular expansion in that series. Let me just show a projection of this plane. So it's a rather busy plot. Again, the density goes like r to the minus gamma at small radii and r to the minus beta at large radii. And I'm just showing the projections of the blue and the green planes. And there are loads of models here that are familiar to people who use galaxy models in their everyday work, such as the Jaffe models or the Dinan models. And they can all be used as zeroth order models to build these basis function expansions. Let me just give a specific example for the NFW model. So the classical Hörnquist-Oestreicher expansion has a general density function, which is the Hörnquist model, times a spherical harmonic, times a Gegenbauer polynomial. And for the NFW, the only thing that changes is that you have a sum of 3 Gegenbauer polynomials. So you can easily make this basis function expansion slick and fast in a code. So let's see how it works. Let's analyze some Milky Way-like dark matter halos. So these have been extracted from a suite of cosmological n-body zoom-in simulations run with gadgets, and they're kind of Milky Way lookalikes. They have masses of the order of 10 to the 12 solar masses and no major mergers since the redshift of 1, and no halos with half the mass of the Milky Way's analog mass within 2 megaparsecs, so they don't have any significant companions. And so the left 3 plots are the simulation, and the right 3 plots are reconstructions with 20 by 12 by 12 basis functions. And so you could see in the top row, for example, the contours are well reproduced by the reconstruction, except every now and then you see a big piece of substructure. There's a big piece of substructure, for example, in the topmost YZ plane, which is not reproduced here. And similarly, it's another example here. The left 3 most panels show the principal planes of the density in an n-body simulation, and the right 3 most panels show the reconstruction of the density using a basis function expansion. And what about the fire halo that I put up at the beginning? So here's a reconstruction with basis functions, and I'm going to put them side by side. So you can see, remember, this box is on a stupendous scale. It's about 500 kiloparsecs on a side. So for the Milky Way halo, we're most interested in representing, say, the inner 200 kiloparsecs. And you see that the basis function expansion does a good job of reproducing the overall mythology within about 200 kiloparsecs. You can also see in the outer parts, there's an aliasing effect, which is obviously associated with the substructure. You can see that the basis function expansion method tries to reproduce some of the substructure. So let me conclude. I think the sets of orthogonal expansions are very rich. In Hörnquist and Oestreicher's paper in 1992, there's this remark, for reasons not immediately apparent to us, this approach has been virtually ignored in the literature, so I think that's correct. And they offer a really powerful technique to encode realistic shapes of dark matter halos, which are going to be needed for a variety of data-driven applications for Gaia or LSST, which will see lots of faint structure about galaxies. And there's a basis function expansion analogous to the Hörnquist-Oestreicher expansion, whose lowest order term is actually the NFW model. So this is still work in progress, We plan to release some code that enables swift computation of the coefficients shortly, but I think it's a very powerful way to think of reducing the complexity of these very expensive cosmological simulations, reduce them into basis function expansions, and those coefficients can be supplied to everyone, and then the codes can be repeatedly rerun with new objects inserted. I think in principle that is the way forward for these expensive galaxy formation simulations. Enough from me. I'm not sure I entirely agree with you, but if you want that basis function expansion, it can be provided. So you want a model that falls off like r to the minus 2, don't you? Yes. So I can produce a Jaffe model which has r to the minus 2 out to an arbitrary large distance and then an r to the minus 4 fall-off. And throughout that r to the minus 2 density profile, the rotation curve will be flat, and again there will be there's a bi-orthonormal expansion that can reproduce exactly that as the zeroth order model.
It's very nice. So when you talk about data compression, though, I wonder, it depends if you want to compress the potential or the density. Have you checked how accurately you really reproduce the density on a sort of location by location basis?
So you raise an extremely good question, which is, what actually does it mean to have a good representation of this embodied model? Is it better to reproduce the density? Is it better to reproduce the potential? Is it better to reproduce the force field? Is it better to look at individual orbits and reproduce the fidelity of those orbits? I actually don't know the answer to that question. I'd be interested to know the answer. We certainly looked at the density and the potential and the acceleration, and we know that the models reproduce the density, potential, and acceleration very well. And we're beginning now to look at individual orbits. So we're taking orbits from n-body models and then integrating them in the reconstructed potential and seeing if, for example, the actions in the apocenters and the pericenters are well preserved. I must admit, for my sort of rather selfish application, I'm more interested in structure in the Milky Way, and for me that's probably more important. But I certainly think the whole question of what does it mean to reproduce the simulation well is an excellent one.
Last question was that.
This is a question about, I mean, this is beautiful and not dull. Very interesting.
Downright dull.
Well, I haven't thought of the adjective I probably should here. But let me ask a question about a possible extension. Because when you're showing the how you do with the fire simulation, the thing that you're missing is some of the very specific structure, the things that look almost point-like, maybe not quite. Now, I've been interested in a similar thing from the perspective of expanding light curves, so looking at time series. And you can use many functional forms that give, nice results that show you the characteristics of one type of physical phenomenon versus another, but lacking in the specifics of really sharp features. So the commonality is these beautiful expansions, in both cases, one spatial, one specifically for time series, but these sharp features are difficult to reproduce. And so I just wanted to see what you had to say about that and whether that's something you're interested in reproducing with your method.
So I think by and large I'm not interested in reproducing that, and I think the reason is probably here. The data that I'm interested in modeling is primarily in this very bright section of the fire simulation. It's within, Gaia will provide data, say, from 20 to 100 kiloparsecs. And there I'm interested in reconstructing the smooth halo very well. so that then I can repeatedly throw in, for example, dwarf galaxies on different orbits with different masses and different inclinations, and look at, say, the tidal features that they produce. You're perfectly correct that the method can't really reproduce these substructures. I must admit, I think the substructure should be removed and then the basis function expansion used to model the smooth underlying dark matter potential. Because I think that's what's generic. If I were to look at a different simulation, the location of this substructure would be different. Right. But I would be interested, for example, in the distributions of these basis coefficients if I analyzed simulation after simulation after simulation. I would hope that they would show, systematic patterns if I looked at the distributions of coefficients.
So, hi everybody. Thank you very much for letting me speak after those really great speakers before me. I think I cannot compete with this. I recently finished my PhD at the University of Heidelberg, and I will be talking today about work which I did back then. So, for my presentation, let's start just with a time outline of the universe, where you have the Big Bang on the left and whatever we have at present days on the right. And the regions I am interested in lie at very high redshifts, at redshifts that we cannot yet observe. So I'm interested in the dark ages and how they become enlightened, so how the first stars and first galaxies started to form, to influence each other with feedback, and then later to reionize. So what is special about those first stars? Well, the first stars form in small structures. They are called Minihaloes, or later they are called the first galaxies, and that's roughly the mass range, so 10 to the 5 to 10 to the 8 solar masses. We unfortunately do not know their mass yet, so we don't know their RMF. But nowadays it's guessed that it's roughly peaking around a few tens of solar masses. The problem is how do we form those first stars? Because at the high redshift universe, we don't yet have any metals, we don't have any dust, we don't have CO. So what we need is we need to see what we can do with what we have from Big Bang nucleosynthesis. And then we have atomic hydrogen, but this only gives us temperatures of about 8,000 Kelvin. And then we have molecular hydrogen, which can go down to temperatures of maybe 150, 200 Kelvin. You can surprisingly do many, many chemical reactions only with hydrogen and helium. So one of the main formation channels of molecular hydrogen actually is via H-, because it cannot form directly. Yeah. So H- is a very, H+ is a very, very important molecule at high redshifts. At high redshifts, you already have some kind of feedback, and one type of feedback that is especially important is so-called Lyman-Werner radiation. And this is UV radiation, which can photodissociate molecular hydrogen, and then when you lose molecular hydrogen, you're basically lost because you cannot cool your gas in the clouds anymore, and therefore you kind of prevent star formation. However, molecular hydrogen can self-shield, and it can also be shielded by neutral hydrogen. And because we have this cutoff energy here, which is below the ionizing limit, you can see that this radiation can travel quite far, so you can build up some kind of Lyman-Werner backgrounds. And this has been studied a bit before, so this is here an old paper where you have different halo masses, and you have first of all, let's look at the case where we don't have any molecular hydrogen in our simulation. Then we basically do not have any mini-halos, first galaxies, that are able to cool below half the virial temperature. So we see everything down here. So basically, no halos are able to cool and later form stars. When you have a simulation with molecular hydrogen, you get quite a lot, but this reduces as soon as you have Lyman-Werner backgrounds. So the Lyman-Werner backgrounds really has this effect of preventing star formation. In my work, I added a small piece to this puzzle, and I asked how much Lyman-Werner radiation can actually be contributed from the first stars and the first galaxies. So I want to kind of study or help to provide a piece of the puzzle for how this Lyman-Werner background is actually building up. And as I said, it's not observable at the moment, so what I do is I run simulations. And what I have is I have simulations in 1D and spherical symmetry, so this is kind of my halo. I put a radiation source in the center, and then I let the simulation run. I use the code SysMP. It has a primordial chemistry network, and I let this simulation run, and afterwards I look what fraction of the Lyman-Werner radiation that is coming from this radiation source here can actually leave this halo. And I do this for a parameter space, so I have two kind of first galaxies with 10 to the 7 and 10 to the 8 solar masses, and I have 5 different SEDs because we don't know about the IMF of the first stars. And I vary the star formation efficiency, so I have different factors with which I multiply. And you can see here that I really exploit a parameter space of different IMS for the SEDs. So I have one that is very extreme, that goes from 50 to 500 solar masses, but others that are more normal and present day like from subsolar to 100 solar masses. So I found in my simulation, in my whole parameter space, I found basically 3 behaviors, and I'll walk you through the first one first. So this case where I have a strong radiation source and I have an immediate ionization front outbreak. So what you can see here is just the mass, fractional mass distribution as a function of radius, and with a solid line, I show you here the density. And this is at the beginning of my simulation, so this is the time axis. And in black, I show you here the radius of the ionization front, and in red, I show you here the escape fraction value. So at the beginning, everything is neutral, and I don't have any Lyman-Werner radiation escaping, because also neutral hydrogen, when everything is just neutral, it can already shield. And then I quickly start to overrun the halo. So you can see here that this ionization front is proceeding, and it continues, and once it has crossed the real radius, also all the Lyman-Werner radiation can come out. So I have this jump to 100% escape fraction here. And then this just stays like this until the end of the simulation. So in the case that I have really an ionization front as this overrunning my halo, also my Lyman-Werner radiation can escape. And then I have this case where, because my SEDs are changing with time, so I have the case where I have an ionization front that is kind of coming back. So here now I show you a different IMF, which goes from 9 to 500 solar masses. So after some time, the most massive stars will die and not provide radiation anymore. And I show you here this behavior again in a similar way. So we start with the same initial conditions. We quickly overrun the halo. But then something interesting happens. So when the most massive stars die and the radiation from those stars doesn't contribute anymore, what happens is that the ionization front is moving back. And then we see a lot of molecular hydrogen building up, and this actually builds up in a very thin shell at the radius of the ionization front, because there you have many free electrons. So you have much H minus, and then you have also much of molecular hydrogen. So you produce kind of this thin shell of molecular hydrogen, which is then able to shield all the Lyman-Werner radiation from the center, so Lyman-Werner radiation cannot reach out anymore. Yeah, and this this fraction of molecular hydrogen grows with time, and it's already too large from the beginning that you can get any kind of Lyman-Werner radiation leaving the halo. So for this kind of behavior, you can just approximate the Lyman-Werner escape fraction by the time that it takes for the halo to recombine from outside in. And then I have a third kind of ionization front behavior, where the ionization front is just moving slowly through the halo. And because I was worried about time constraints and I don't want to take too much of your time, I just show you the result here. So sometimes when the ionization front is just moving very slowly through the halo, you have only a little bit of molecular hydrogen always forming where your ionization front is, and then this provides some shielding against Lyman-Werner radiation, but the Lyman-Werner escape fraction is always very dependent on the exact microphysics, on how much molecular hydrogen you can form, what the fraction of ionizing photons to Lyman-Werner photons is. Yeah. And with this, I would like to leave you with my conclusions, and I hope you have some questions for this very specific talk.
Questions?
You broke this types of movement in these three categories. Do you have any sense of like how often do you expect each, like in some population of minority inhalers for that to occur?
Yeah. So I think the one case where I have the overrunning ionization front is too extreme. It's my maximum case. So what I actually think is that most of my simulations show that maybe you have a general escape fraction of something 20 to 70%. So you will always have either this case with a slowly moving ionization front, or when then the stars have died and not new ones have formed of that masses, that you have the case of the returning ionization front. So I think those are the more probable cases.
Anna, to put this in a bigger context, the question that you're addressing is important to figure out whether the first stars were of academic interest or of importance to the universe, because if a little bit of the Lyman-Werner radiation can escape and basically destroy all the molecular hydrogen, then the very first stars were a very small population.
Yes.
Produce much ionizing radiation. And then you have to wait until much bigger galaxies form and they ionize the universe. However, if not much of the Lyman-Werner escapes, then of course you could make many more stars in those molecular hydrogen halos.
Yeah, exactly. And in addition, the Lyman-Werner radiation is not the only kind of feedback or effect that influences the formation of the first stars. So it's a small field, and we need to come from many sides and from many points of views to combine this knowledge to then hopefully at some point derive 21 centimeter predictions.
Yes, well, some of us hear rumors that there might be some interesting results on 21 centimeter in not so distant future. So
That's exciting. Thank you. I just put it there.
Yeah, you sounded great. Okay. So does the mic work? It's okay? Okay. So as disparate as the topics are between Anna and myself, where did it go? So as disparate as the topics are, I have exactly the same remarks to make at the beginning. I want to thank the organizers. I want to say what a challenge they've given me, challenging acts to follow in terms of the talks before me. And also I want to mention this is work done back when I was a graduate student, this time at Columbia, and I should have attributed my co-authors, my advisor Mu-Dao Wong and my fellow graduate student now moving to MIT, Pei-Ken Hung. So I'm talking about sort of a very classical topic that might seem like as though it's resolved, but sort of looking at it from a more mathematical GR perspective and seeing sort of what's changed between the 1970s and now. Okay, so just to outline the next 10 minutes, I just want to reintroduce the Schwarzschild solutions. Everyone's seen these, and talk about the black hole stability question and why we might again consider reconsidering it. The sort of view we adopt is that many of the people in the physics community understood the geometric and algebraic character of Einstein equations very well, even back in the 70s. And so we're going to be relying upon a lot of the technology they produce. The Reggie-Wheeler and Moncrief-Zerilli equations are sort of the workhorse of the method we adopt. And then I'll talk about, again, sort of the modern analytic view we could take on these equations and sort of how the analysis of them could proceed. Okay, so again, in very, very standard Schwarzschild coordinates, the Schwarzschild metric appears as follows. You notice that it's a static and spherical symmetric spacetime, so it's somehow the next nicest thing to Minkowski in terms of being highly symmetric, and somehow finding it as a solution involves just looking at radial ODEs. The coordinates I've given you have this coordinate singularity at r is equal to 2m. My goodness, at r is equal to 2m, and in fact there are extensions beyond such discovered by Singe and Kruskal, which allow one to go within this black hole region, which has all this bizarre geometry. So the Schwarzschild solutions were not just dreamt up as a metric. In fact, they solve these Einstein equations. They're one of the simplest non-trivial examples of such. And again, they in terms of maximal extension, they display some very, very bizarre behavior. You might wonder whether this behavior is an artifact of the high degree of symmetry or whether it's actually a genuine phenomenon, in particular the black hole physics. So sort of whether these things are stable as solutions of Einstein equation, and also in what sense they're stable. These would both be sort of important questions to address. So the old sort of physics approach was to look at linearized gravity and to simply consider solutions with very particular time dependence. You might consider solutions e to the I omega t down here, and try to rule out these exponentially growing modes. So modes with omega having imaginary part negative, you might try to rule such things out. On the, you sort of also have this interesting discussion of quasi-normal modes, which gives some sense of the ring down, and I know that's important. Also, in terms of doing this study, a number of people made great contributions. I mean, there was Moncrief-Zerilli, there's Reggie-Wheeler, in terms of sort of metric level quantities that they discovered. There was also Bardeen and Press. And later Tucholsky, they discovered some sort of wild curvature component that sort of naturally satisfied a nice equation to study. So in terms of the algebraic and differential structure, a lot of it was elucidated in terms of this sort of mode stability analysis that was done earlier back in the 1970s. So from a more modern point of view, in the mathematical community, we're way behind. The only thing that's been done so far, really, or the most well-known result, is the stability of Minkowski space. And if I think about it from the old physics perspective of just studying linearized gravity, it's completely boring. It's simply just the wave equation. And this is just the most obvious thing in the world. So how did it take these two people 520 pages to write out this result, and take until the mid-90s? And the point is that they're not just considering linearized gravity, they're actually considering the sort of the big enchilada. They're considering the nonlinear structure of Einstein's equations. And again, to talk about whether these things are stable, I think that the mode stability and linear stability more generally are considered good indicators, not quite smoking guns. But for anyone who's not a radical skeptic, those are, I don't think anyone believes at this point that Kerr is unstable, or that what EHT is looking at is not the black hole in the center of our galaxy. So in what sense, though, and maybe the value of Christou Klotterman, they give a more precise sense of how the thing is stable. And it does have a few sort of ramifications within non-mathematical communities. So in particular, they're following a bunch of quantities in a very precise way all the way to null infinity. And as a consequence, Christodoulou a few years after sort of discovered that nonlinear memory was actually going to be sort of large and maybe of a similar size to the sort of linear memory effect that had already been found in the 70s. And so maybe not my grandchildren, but my grandchildren's grandchildren, the LIGO at that time will be looking for this. There's also some recent thing in the high energy physics community with sort of BMS symmetries and charges, where again, Christou-Kleinerman's result sort of overturned the sort of Penrosian peeling estimate conventional wisdom and allowed people to see these things for the first time. So more recently, so maybe in the past 10 years, we've gone beyond Minkowski space. We've sort of come out of our caves, and we're actually starting to look at curved spacetimes and be able to do estimates on them as well. In particular, I guess I should mention, we have sort of, in a perturbative regime, we're starting to understand spacetimes that are close to FLRW, Schwarzschild, Kerr, cosmological generalizations, Reiser-Nordstrom, Kerr-Newman, et cetera, et cetera. And so the basic research program is to first just look at test fields, and again, we're always looking for dispersion of these waves. Then we might consider the linearized problem, and finally we might consider, again, the full sort of problem on the spacetime. So I'll be talking about this adapted to the Schwarzschild spacetime. And as I mentioned, the general thing to do is to look for dispersion. So now we're linearizing the Ricci tensor, and we're considering delta G as sort of a 2 tensor on the background Schwarzschild, and naively wondering about its dispersion. There are some caveats. I mean, of course, Einstein's equations are diffeomorphism invariant, and sort of the linear level that manifests itself with these pure gauge solutions. So X a covector field representing an infinitesimal change of coordinates, then its Lie derivative of the Schwarzschild metric winds up being a pure gauge solution. So these things won't disperse in general. Moreover, Schwarzschild is contained in the larger Kerr family. We know about the stationary axisymmetric solution with sort of this extra angular momentum parameter. It's always possible to move within this family without anything going so awry. This is totally natural. And so the real statement is not just that delta G should attenuate or disperse. It's that after normalization by a particular gauge solution, then it should decay maybe to another member of the Kerr family, the linearized Kerr family. So in terms of what makes this possible, it's that the Schwarzschild background on which our tensor lives is spherically symmetric. And so we sort of can use or do some sort of Hodge decomposition that was recognized way back in the 50s by Reggie Wheeler, maybe in a more, I would say, clumsy way. So for a spherical covector, the way this looks is I can always decompose it into two potentials, V and V underline. And the sort of story behind this is it almost is a sort of Hodge decomposition, you might think, if you remember your differential topology. So we've written V down as an exact plus a co-exact differential, differential forms mapping up to it. For symmetric choices, two tensors, there's some similar thing. This TAB can be written in terms of a covector potential, and then we can apply the previous covector decomposition of TAB, and find again two scalar functions W and W underline, which T can be expressed in terms of, so two potential functions. Now, in terms of how this applies to the stability analysis, the linearized metric and the linearized Ricci tensor are both objects on the Schwarzschild background. Every time I see a spherical index, I can simply, if it's just one spherical index, I just split it as a covector. If I have two spherical indices, I take the traceless part, and split it according to the second formula. And so what it does is it splits things into closed and co-closed subsystems, and this makes the sort of very complicated linear system easier to study. We just study each of the pieces. So for both the pieces, there's sort of, one approach is to use this sort of Reggie Wheeler Moncrief-Cirilli equations. These are sort of well-known master quantities which decouple and satisfy nice wave equations. I guess I should mention they're gauge invariant. We can write them as some symmetric traceless two tensor quantities. And moreover, they're defined in terms of the linearized metric and its first derivatives. So the first, the simplest, is the Reggie Wheeler equation discovered way back in the 50s. It has this nice potential, this V minus, which is a nice positive quantity. I'm sort of sweeping some things under the rug with this D'Alembert operator, this wave operator with this slash through it. What's going on there? There's sort of complicated business with this thing living on a tensor bundle. So anyway, with the closed piece, things are a little bit more complicated. We actually need to use a tensor spherical harmonic decomposition. And gradually we find a rather less pretty equation with sort of a nasty potential. I've just written down this N compactifying some of the harmonic notation. Of course, if you're a very pedantic person, and we have in our paper, you can write it out in terms of inverse elliptic operators and so forth and so on in the sphere. And so these two equations, which again were discovered, I would say Moncrief-Cirilli was discovered way back in the 70s in a nice gauge invariant way. These are sort of the workhorse of our method. So in terms of both equations, we have, from Noether's theorem, Well, we have a static Killing field. That is to say, we have a symmetry of the background spacetime. And so we get a conserved energy. So we can think about, time 0, we compute this energy, it's finite. Then for all later times, it will be finite since it's equal. You notice that the energy bounds the t derivative term then, because these v plus minus are positive, we can throw away all these other terms, keep the dt term. For mode solutions, then we could not possibly have some sort of e to the alpha t with alpha positive. So we can rule out exponentially growing mode solutions and find mode stability. On the other hand, the energy is not so great. It actually turns out it degenerates at the event horizon. This has to do with the causal structure of t, it becoming null there. And so, in terms of these recent developments I told you about in the community, people have figured out how to construct a strictly time-like multiplier, this redshift vector field. And somehow what it does is it corrects for t's degeneration to something null in the event horizon by using more or less the positive surface gravity of Schwarzschild. So this is very nice in the sense that it can be generalized to Kerr, well, sub-extremal Kerr. So even with a non-degenerate energy, this is my last slide, sorry. Even with a non-degenerate energy, which remained uniformly bounded, we wouldn't really have dispersion. We wouldn't really be exactly where we wanted to be. So we need to keep going a little bit further. In terms of dispersion, it's actually quite complicated because we have this photon sphere that's well known to Schwarzschild, where these null geodesics are trapped. And the null geodesics are characteristic curves of the wave operator that we're working with. So we can imagine then solutions of these wave equations being localized. Start with a small bump that's near r is equal to 3m, evolving it. Now it could remain uniformly bounded and not in violation of this previous remark I made about this non-degenerate energy. On the other hand, it could remain localized to this r is equal to 3m and not disperse. So it makes things difficult to spread. Back in the 60s, there was a mathematician named Morowitz, actually Singe's daughter, who came up with a way to get around this sort of convex obstacles which sort of represent this situation in Minkowski space. And more recently, a number of people, Avi Loeb, DeFermos, Rodniansky, have managed to generalize this to curved spacetime settings like Schwarzschild and Kerr. So in the end, we can find some dispersion estimate and some nice decay of these q plus and minus, given that they satisfy the Reggie-Wheeler and Moncrief-Zerilli equations. And from there, we're not really quite done yet. We need to estimate the linearized metric, and so we just need to relate these two back to the linearized metric by imposing an appropriate gauge. Okay, and that's it. Thanks for your attention.
Mm-hmm. The fact that there's favored, at the end, would that be a proof, or you really need to go through the math?
But that's a little bit complicated though, because as far as I understood it, the in-spiral phase is way. I mean, the two-body problem or whatever, the in-spiral phase, we're way far away from analyzing that. Maybe just the ring. You're talking about the ring down or something like this.
Yeah.
I mean,
there is no instability.
Yeah, even though it should be extremely violent after the yeah. I suppose that's fine, and in fact it's vacuum. So yeah, no, that is some good, maybe not a smoking gun. Again, people are radical skeptics, me amongst them. So, but yeah, no, you're. No, the jury's still out.
We haven't seen the ring down there.
That's right. So you don't know if it's a black hole at the end?
We haven't seen the metric ring down. We haven't seen normal modes of the geometry. That the signal noise is not good enough.
Right, but if it was an unstable object at the end, wouldn't you see something? Not necessarily.
Well, you would see something different than what we've seen now. But I can't prove that we've seen the normal modes, and that the normal modes don't have to answer. I mean, that's one of our ambitions. You asked what
In the future. Mm-hmm. Any other comments or questions to John? If not, let's thank all our speakers.